Hello everyone, today we are going to analyze the abalone dataset, a supervised regression problem, where the goal is to predict the age of abalone using physical measurements. We will discuss the key data preprocessing and modeling steps, evaluate different models including their biases, variance trade-off, and reflect on the insights from the results. I will proceed with the analysis in the order specified by machine learning workflows. At the beginning, we imported a comprehensive set of libraries for data preprocessing, model training, validation, and evaluation, include linear models, tree-based models, and ensemble methods. Then we come to the first step of machine learning, data acquisition. The dataset was retrieved from the UCI machine learning repository using Python's USML report package. It contains 8 features: sex, length, diameter, height, hole weight, shaft weight, throw weight, and shear weight. The target variable is rings, which corresponds to age, and we can know from the interpretation that the age is equal to 1.5 plus the number of rings. The second step is data exploration. We can find that the dataset was clean and has no missing values. Also, there are no duplicates. Exploratory analysis also shows that several features like hole weight and shaft weight are right-skewed, which may impact linear models more than tree-based models. At the data preparation stage, categorical feature sex was encoded using label encoder so that machine learning models can process them. Outliers in the target variable were removed by using the Tukey rule to improve model reliability. We split the data into 80% training and 20% testing to evaluate model generalization while avoiding data leakage. Also, features and targets were standardized using standard scalar to bring them to similar scales, which is important for models like KNN, SVR, and MLP. At the feature engineering stage, feature importance was assessed using a random forest regressor. Feature important plots highlights that shear weight is among the strongest predictors, reinforcing domain knowledge about abalone growth. All features contributed meaningfully, so no feature elimination was performed at this stage. Then we turn to model selection. A range of supervised regression models was evaluated at this stage. Linear regression, lasso regression, ridge regression, elastic net regression, KNN, SVR, decision tree, and multilayer perception. Performance metrics include MSE, MAE, R-square, and the maximal error. We can find that it doesn't evaluate logistic regression. Although logistic regression is not applied here due to the continuous target, conceptually it would have high biases if age were discretized, leading to information loss compared to regression models. One drawback of this machine learning process is that, strictly speaking, this workflow doesn't include a separate validation set. We can see that it only has train set and test set. However, the holdout test set is used to evaluate generalization performance and compare models, which fulfills a practical role of validation in this assignment. Ideally, a separate validation set or k-fold cross-validation should be used for hyperparameter tuning to avoid optimistic biases. In this assignment, the holdout test set serves as a proxy for validation when comparing models. Next, we will discuss model selection in detail. Linear regression and ridge regression perform best according to MSE and R-square. The MSE of linear regression and ridge regression is equal to 5.1. The R-square of linear regression and ridge regression is equal to 0.53. Although linear regression and ridge regression achieve nearly identical test MSE and R-square, ridge regression is preferred because it balances biases and variance better. The predicted BS actual scatter plots shows that ridge regression predictions align more closely with the diagonal line compared to other models, supporting its superior generalization performance. The Bologna dataset contains highly correlated physical features, such as length and multiple weight measurements. Ridge regularization reduces coefficient instability caused by multicollinearity, lowering variance without significantly increasing biases. Therefore, ridge regression offers better robustness and generalization. In contrast, lasso regression shows very low R-square, indicating high biases due to excessive coefficient shrinkage. Decision trees, while flexible and capable of modeling nonlinear relationships, demonstrate poor test performance with a lower R-square and higher MSE, consistent with their nature as lower bias, high variance models that are prone to overfitting. Neural network models such as the MLP achieve comparable performance with an R-square of approximately 0.51, but do not outperform ridge regression. This suggests that the additional model complexity increases variance without providing sufficient gains in predictive accuracy for this dataset. There are some implications for real-world applications. Age prediction of abalone can be automated using a few measurable physical features. Ridge regression provides reliable predictions without extensive data preprocessing. This can support features and ecological studies by reducing the need for invasive age estimation. Feature importance analysis highlights which measurements most influence age, guides data collection efficiency. In conclusion, the ridge regression model effectively balances bias and variance for the abalone dataset. Future improvements could include cross-validation and ensemble models such as random forests to further enhance predictive performance. Thank you.